Welcome to an extraordinary journey into the heart of darkness, where time and space become distorted, and the laws of physics as we know them cease to exist. In this captivating exploration, we will delve deep into the secrets of these cosmic powerhouses, shedding light on their origins, behavior, and mind-bending properties. Imagine a colossal star, billions of times more massive than our Sun, reaching the end of its celestial life. What remains is a stellar remnant, so dense and compact that not even light can escape its gravitational grasp. This is the birth of a black hole. Imagine a colossal star, billions of times more massive than our Sun, reaching the end of its celestial life. What remains is a stellar remnant, so dense and compact that not even light can escape its gravitational grasp. This is the birth of a black hole. As we approach the event horizon, a point of no return, we enter a realm where the laws of physics bend and twist in ways unimaginable. Time slows down, and space itself becomes a warped tapestry, as the black hole's immense gravity distorts the very fabric of our reality. Approaching too close to a black hole would subject anything or anyone to a process known as spaghettification, a stretching and elongation caused by the extreme tidal forces. It is a visual reminder of the immense power contained within these cosmic behemoths. But black holes are not just cosmic devourers. They are also engines of creation. In their vicinity, swirling disks of superheated gas and matter form, generating tremendous energy. These accretion disks and the jets they produce can reach mind-boggling speeds, shaping the very structure of the cosmos. Throughout history, scientists and astronomers have tirelessly sought to unravel the mysteries of black holes. Through groundbreaking research, ingenious theoretical frameworks, and astonishing technological advancements, we are now closer than ever to understanding these celestial enigmas. Join us as we embark on this extraordinary voyage of discovery, where the boundaries of our knowledge are pushed further, and our understanding of the cosmos is forever expanded. Brace yourself for a thrilling exploration into the captivating world of black holes. Prepare to witness the unimaginable. Certainly, black holes are fascinating cosmic entities that are formed from the remnants of massive stars. To understand them, let's dive deep into their nature and properties. At the heart of a black hole lies an incredibly dense and compact region called the singularity. This singularity is thought to be a point of infinite density and zero volume, where the laws of physics as we know them break down. It is surrounded by an invisible boundary known as the event horizon, beyond which the gravitational pull of the black hole is so intense that nothing, not even light, can escape its grasp. Black holes are formed through a process known as gravitational collapse. When a massive star reaches the end of its life, it exhausts its nuclear fuel and can no longer sustain the outward pressure generated by the nuclear reactions in its core. Without this pressure to counterbalance gravity, the star collapses under its own weight. The collapse of the star depends on its mass. For stars that are several times more massive than our Sun, the gravitational collapse is so powerful that it leads to the formation of a black hole. This process is known as a stellar black hole. On the other hand, less massive stars can become white dwarfs or neutron stars after their collapse. The size of a black hole is defined by its event horizon, often referred to as the point of no return. Anything that crosses this boundary is trapped forever, unable to escape the intense gravitational pull of the black hole. The event horizon is typically a spherical region surrounding the singularity, and its size depends on the mass of the black hole. The more massive the black hole, the larger its event horizon. While black holes themselves do not emit light, they can be detected through their interaction with surrounding matter. When matter, such as gas or dust, falls into a black hole, it forms an accretion disk, a swirling disk of superheated material that spirals inward due to gravitational forces. As the matter in the accretion disk interacts and collides, it releases an enormous amount of energy in the form of X-rays and other high-energy radiation. These emissions can be detected by telescopes, allowing us to indirectly observe black holes. Black holes also possess another remarkable feature. Their strong gravitational fields can cause the distortion of spacetime. This phenomenon, predicted by Einstein's theory of general relativity, is known as gravitational time dilation. Time near a black hole appears to slow down compared to time in regions of weaker gravity. This effect becomes more pronounced as one gets closer to the black hole's event horizon. Additionally, black holes have the ability to generate powerful jets of particles and radiation. These jets are believed to originate from the accretion disk, where intense magnetic fields interact with the infalling matter. The jets can extend over vast distances, shaping the surrounding cosmic structures and releasing enormous amounts of energy into the universe. Studying black holes is a complex and ongoing endeavor for scientists. Observations from various telescopes and space missions, such as the Hubble Space Telescope and the Chandra the 10th Ray Observatory, have provided valuable insights into their behavior and characteristics. Scientists also employ sophisticated mathematical models and computer simulations to better understand the dynamics of black holes and the fundamental physics that governs their existence. In summary, black holes are celestial objects born from the remnants of massive stars, with an extreme gravitational pull that prevents anything, including light, from escaping beyond their event horizon. They possess a singularity of infinite density and are surrounded by accretion disks that emit intense radiation. Black holes challenge our understanding of the universe and continue to captivate scientists, driving further exploration and discoveries in the realm of astrophysics. A singularity is a term used in physics to describe a point or region where certain quantities become infinite or undefined. In the context of black holes, a singularity refers to the extremely dense and compact core that lies at the center of a black hole. According to our current understanding, the singularity is thought to be a point of infinite density and zero volume. It represents a breakdown in our understanding of the laws of physics, specifically in the realm of general relativity, which describes the behavior of gravity on a large scale. The singularity is located within the black hole, hidden behind its event horizon, the boundary beyond which nothing can escape. Due to the intense gravitational pull of a black hole, all matter and energy that enter the event horizon are inevitably drawn toward the singularity. As an object collapses under its own gravity to form a black hole, the matter becomes increasingly compressed and packed into a smaller and smaller volume. The singularity is the result of this extreme compression, where the density becomes so incredibly high that it reaches an infinite value. However, it's important to note that our current understanding of physics breaks down at this point, as our theories cannot fully describe the behavior and conditions within the singularity. The concept of a singularity arises from the equations of general relativity, which predict the existence of a point of infinite density at the center of a black hole. However, scientists believe that the singularity is not a physical reality, but rather an indication that our current theories are incomplete. It signifies the limitations of our understanding and points to the need for a more comprehensive theory, such as a theory of quantum gravity, to fully describe the behavior of matter and gravity under such extreme conditions. It's worth mentioning that the singularity is often considered to be a mathematical concept rather than a physical object that can be directly observed. It lies beyond the reach of our current technology and observational capabilities. Nonetheless, scientists continue to explore theoretical frameworks and conduct research to gain a deeper understanding of the nature of singularities and their role in the cosmos. In summary, a singularity is a hypothetical point of infinite density and zero volume that lies at the center of a black hole. It represents a breakdown in our current understanding of physics, specifically in the context of gravity. While the singularity is not directly observable, its existence is predicted by our mathematical models, and further research is ongoing to unravel its mysteries and develop a more complete theory of the cosmos. The mathematics of black holes involve several key concepts from the field of theoretical physics, particularly Einstein's theory of general relativity. General relativity provides a mathematical framework for understanding the behavior of gravity and its effects on spacetime. To delve into the mathematics of black holes, we'll explore a few fundamental concepts. Spacetime and curvature. According to general relativity, gravity is not just a force, but rather a curvature of spacetime caused by the presence of mass and energy. Spacetime is a four-dimensional continuum that combines the three dimensions of space with a dimension of time. The curvature of spacetime around a massive object, such as a black hole, is described mathematically using a set of equations known as Einstein's field equations. The metric tensor. The metric tensor is a mathematical object that describes the geometry of spacetime. It specifies the distance between nearby points in spacetime, taking into account the curvature caused by the presence of mass and energy. The metric tensor is used to calculate various properties of black holes, including their event horizon and singularity. Schwarzschild solution. The Schwarzschild solution is a mathematical solution to Einstein's field equations that describes the spacetime around a spherically symmetric, non-rotating black hole. It was first derived by Carl Schwarzschild in 1916. The solution is parametrized by a quantity called the Schwarzschild radius, which determines the size of the black hole's event horizon. The Schwarzschild solution provides a mathematical description of the geometry and gravitational field of a non-rotating black hole. Singularity and event horizon. The singularity and event horizon are important mathematical concepts associated with black holes. The singularity is a point of infinite density and zero volume that lies at the center of a black hole. The event horizon, on the other hand, is the boundary beyond which nothing can escape the gravitational pull of the black hole. Mathematically, the event horizon is determined by the Schwarzschild radius, which depends on the mass of the black hole. Kerr solution. The Kerr solution is an extension of the Schwarzschild solution that describes the spacetime around a rotating black hole. It takes into account the angular momentum of the black hole, introducing additional mathematical complexities. The Kerr solution provides a description of the geometry and gravitational field of rotating black holes and allows for the calculation of properties such as the Regesphere and the rotation rate. Penrose diagrams. Penrose diagrams are graphical representations of the spacetime geometry of black holes. They allow for a visualization of the causal structure and the paths of light and matter near and inside a black hole. Penrose diagrams provide a useful tool for understanding the mathematical properties of black holes and their relationships to other regions of spacetime. These are just a few examples of the mathematical concepts and tools used in the study of black holes. The mathematics involved in black hole physics can be highly complex and requires a deep understanding of differential geometry, tensor calculus, and advanced mathematical techniques. Researchers in the field continue to explore and develop mathematical models and techniques to better understand the properties and behavior of black holes. Goodbye.